So the topic for today is to discuss maximum likelihood estimation. So that's the big overall topic. And of course, we are particularly interested in maximum likelihood estimation because we want to use it to estimate the parameters of the GLM, which, as you, I guess, know now, are the beta parameter and the variance term of the error. So this is where we are in, with respect to the GLM, and we want to estimate the beta parameters and the sigma square parameter now. But before we actually look at how this is done in terms of the GLM, I want to introduce maximum likelihood estimation also in a little bit broader context, because it's really a method to obtain parameter estimates in any kind of model, or let's say in any kind of probabilistic model, where you can actually write something down like a likelihood function. And it's also fairly popular in models that I guess you are learning about now in other courses, so behavioral models, where people have some idea about how to model some behavioral data, and then they usually use maximum likelihood estimation and maybe then some model selection criteria to determine which model explains the data best. And so it's really a general framework for modeling in the cognitive neurosciences and of course beyond. And yeah, so I want to also give you that perspective so that we not only focus on the parameter estimates in the GLM, but also in the more general context of model estimation. So the first thing that we have to do, I'm afraid, is to do a calculus refresher. I will do this in a example-based manner. So you have some notes for those who haven't done any derivatives and finding the maximum of a function in the last 3 or 4 years. It would be a good idea to work through the notes that you have on calculus. I will here discuss a brief refresher, which just has to be done. Otherwise, for those who haven't seen this for 3 or 4 years, the rest will not really be meaningful. So for those who have done this over and over in the last 3 years, bear with me and maybe help your colleagues. Then the next thing will be, kind of the maximum likelihood estimation method, if you want. So there we will discuss the general idea and some aspects of it that are important. So that's what you have in the script in chapter 8 overview. And then we will do an example which is very closely related to the GLM, but also which can be considered outside of the GLM. And we will do that then as the final thing. So why do we have to do this calculus refresher? Well, the main reason is that maximum likelihood estimation implies that we maximize a function, so that we find the maximum of a function. And this, maybe I can tell that already now, can be done in 2 ways. This can be done analytically and numerical. Or numerically. Maximum likelihood estimation can be done analytically and numerically. And the analytical way is what you what is important in the context of the GLM, because analytical solutions exist, and in all kind of nice and small and mathematical tractable small examples. So essentially, you need the analytical approach to understand model-as estimation in the GLM and small examples. And by analytically, I mean the thing of evaluating the maximum of a function by doing what you know from calculus, so computing derivatives, setting to 0, and so on. Another way to do maximum likelihood estimation is numerically, this is actually a very broad field in somehow in cognitive neuroscience. What survives for some reason is MATLAB's fmin search, which implements a specific gradient-free optimization algorithm. And this is usually derivative free. However, there are also many nonlinear optimization in mathematics, and applied mathematics is a big field. So there are also a lot of forms and also a lot of things in the numerical approach that are highly inspired by the analytical approach. So you will not really be able to understand convergence criteria of numerical approaches if you don't know what analytical maximization of a function means. So although some of you might think, oh, maximum likelihood estimation, why do we have to talk about a calculus again? I can do it with fmin search. Yeah, if that's your approach to life in general, that's fine with me. But so I think there's a lot of value in talking about the analytical part as well. Hence, we will have to do a little bit of a calculus refresher, and we will, like I said, do that in terms of an example. So we start with the example now. Questions at this point? No. Good. So we are now going back to your high school days, where you dealt with functions in mathematics that maybe look like this, and this will be our working example. X minus 3 square plus 4 and a minus sign in front. And then what you did, or at least we did when I was in school, was something called Kurvendiskussion. So basically the task was to basically plot the function and learn something about its important values. So who remembers in high school finding minima, maxima, or other critical or interesting points of these kind of functions? Who did that in high school? Is there anyone who did not do that? You're not sure. Well, then it's unlikely that you did not do it, because you will remember that forever if you did it. I mean, we did it for like a year or so, or 1.5 years. It just went on and on and on. Anyway, good. So then maybe let's see when we actually do it, whether you have more of a feeling that you have seen that before. So a first thing that you can always do, and you should also always do now that you will soon know how to program, is actually to look at the shape of the function. And in this case, because the function is just mapping real numbers onto real numbers, so everything is one-dimensional, that's fairly easy. Or well, easy, I don't know, but it's easy to visualize at least. It gets harder if you have multivariate functions. And to do so, yeah, we can first plot it. And the way I learned it in school is that you first make a table where you yeah, basically evaluate the function at certain values. And this is the same thing you will have to do in a computer. So you have to specify some input arguments and evaluate the output arguments. So let's do that now. So if you put 0 into the function as x, what is the output? -5? I guess, no? 0 minus 3 is minus 3 squared, and then minus plus 4 is -5. Okay. 1? 0, because this is 2, yeah. 2? 2? 3? I also think so. 3? 4? 4? 3? And 5? 0, because this is 2, this is negative, and then 0. Yeah. So based on that, we can actually now already plot it. So let's make a plot. Maybe like this. 1, 2, 5. Oops, the 5 is a bit far out. 5 and 1, 2. Well, the scaling is not optimal, but of course in real life I would do this with the help of a computer. And then, so basically what you have to do is annotate the values. So we had -5 for 0, 0 for 1, 3 for 2, 4 for 3, 3 for 4, and 0 for 5. And then you can interpolate by connecting the dots, which is of course a highly risky issue, because you might be wrong with what you are doing here, but I don't get the... That's more beautiful. Well, this is why I use a computer in general to do that. So I think that's the best I can get it this morning. Yeah, so now you have actually plotted the function. That's good, and you will shortly know how to do that with a computer, and then of course it looks nicer. And then the task in school was to find the maximum and I guess also the value where the function takes on its maximum. By looking at the function, what do you guess where the maximum of the function is in terms of x? At 3. And what is the value that the function takes on at the maximum?
4.
Yeah. That's also what I think. The way you were used to do that in school, I hope, is that you went through a particular procedure. Does anyone remember the procedure to find the maximum of a function? Yeah, why is taking the derivative and equaling it to 0 a good idea? It's just the way to do it. Yeah, actually there's some explanation of why that is a good idea in the script. So if you maybe if you remember that a derivative is something like the slope at a given point, so you can draw the slope like this, then at a maximum the slope is actually 0, so the derivative is actually 0. So finding that the derivative is 0 at a certain point is a necessary condition. So if so read about the details why this whole procedure works in the script. where I think I documented it quite well. And quite detailed, and also what a derivative is in general. But here I want to, just in terms of the example, again, do this thing that you're familiar with in terms of following a procedure. So the first thing that you said is to compute the derivative of the function, set it to 0, solve for the point where this is the case. And there's one additional thing that you need to do for maxima and minima. Take the second derivative and check whether it's larger or smaller than 0. And then there's this nice thing that if it's smaller than 0, then it's a maximum. If it's larger than 0, it's a minimum. Also, that is explained in more detail in the script. So, yeah, then let's do that. So, without explaining what a derivative is, I'm just denotating the derivative now here with this f prime. Maybe I do it in red, then it gets more attention. So f prime, you now have to compute the derivative of the function that is defined here. Any suggestions from those who haven't done this in the last 3 years? Do you remember anything about computing derivatives?
I think you have to use the chain rule.
You have to chain rule, yeah. What does that mean?
It means like when two functions are connected into each other.
Mm-hmm.
But I don't remember the exact rule.
Okay. Yeah, exactly. So one thing, and this is also documented in the script, the first thing is that computing derivatives is a linear operation. So you can first compute the derivative for this term and then compute the derivative for this term. And what you actually need here is the chain rule. So you have the square function, and in that you have the function x minus 3. What the chain rule essentially says is that if you compute the derivative of nested functions, then you have to compute the derivative of the outer function and have it at the location of the inner function, and then multiply it with the derivative of the inner function. That's what the chain rule says, so you can also read about that in the script. What does that mean for this term here? Now the people that have done this in the last 3 years? Yeah, I want you to take the derivative. So we leave the minus.
X minus 3. And the derivative inside is 1.
So it's times 1, which is the chain rule, so that goes away. And the derivative of this constant 4 is 0. Yeah. So that's in fact the derivative. While we are at it, we might as well compute the second derivative as well. So the second derivative is the derivative of the first derivative. And maybe you could, it's minus 2 because it's a little bit easier if you multiply this out, then it's really easy to see, but it's also can seem like that. So if you have no idea how these derivatives are computed here, that's fine. But have you seen these things? Who has not seen this ever to happen? So everybody has seen this to happen. Okay, so then I think you're well versed to look into the calculus stuff that I wrote up if you want to refresh how it works in detail. Okay, so that's good. So we now have the derivatives, and then we have our procedure to find the maximum of a function. So the procedure was, as discussed previously, let's take different color here. The procedure was to set the first derivative to 0, which in this case then means that we have to set our minus 2x minus 3 to 0. And what actually is happening here, that this is kind of this xc, maybe we'll give it a little star. That's the point that we are actually looking for. So now we can solve that, and I'm sparing you to have to tell me what happens. So I do it briefly. So it's minus 2x star. So we take the 3 on the other side. I forgot the brackets. Very good. So we have actually I wanted to multiply it out, but I did it wrongly. So this is what I wanted, right? So I wanted to do minus 2x times minus 3, which is plus 6. And then we take the 6 on the other side, and then it all makes a lot more sense. So we have minus 6 on the other side, and then we divide by minus 2, and we get minus 6 divided by minus 2, which is 3. And we find that indeed our the point where the function assumes its maximum is here at x star equals 3, because we also know that the second derivative is always negative. So regardless of the value of x, it's negative. So we have a maximum. One thing that is important to dissociate also what we need in the remainder is that there are two things interesting with respect to the maximum. One thing is the location where the maximum is taken on. That's a point in the input or the domain of the function, which is here 3. The other thing that is of interest is the value that the function takes on at the location of the maximum. That's here 4, which you can get by plugging in 3 again, and we did that already, and we have this here. Okay, so that was the calculus refresher. So essentially, you know a procedure how to do that. You might want to look into that again. One thing, of course, about this procedure is that I chose, and also in school, you usually dealt with functions where things are relatively straightforward. And for example, in this case, a function that actually has a unique maximum. Of course, if the functions get more complicated or more involved, then also being certain whether something is a maximum or not a maximum or saddle point and so on gets more involved. Nevertheless, these kind of squared functions, so we have a square here, obviously, there. They are quite important also in maximum likelihood estimation, because often the likelihood functions that are to be maximized actually involve a square. So if you remember that we, for example, in the Gaussian, there's this square term. This then carries over also into maximum likelihood estimation in a certain form, as we will see. So actually, these kind of what is called concave functions play an important role. And also surprisingly, you will often find in the applied literature, which we will also see later, is that actually the second condition, whether the second derivative is actually larger or smaller than 0, is not actually checked. So this is something we will see when we compute the maximum likelihood estimates for the n samples from a Gaussian distribution. We will actually not deal with the second derivative, which is fine if you have proven first that you're actually dealing with a function that looks like that. So that's something that is somewhat absent also from the statistical textbook literature. Okay, so questions about this calculus refresher right now? No. Good. Then we can now talk about maximum likelihood estimation. And that's what we're going to do. Or let's call it maximum likelihood, simply. Okay, so maximum likelihood estimation is a very general procedure that can be used to estimate parameters and obtain point estimates for parameters in probabilistic models. And it's called maximum likelihood because what one looks for is a value of the parameters that maximizes the so-called likelihood function. So maybe I write up a couple of terms that we have to discuss now. So first we have to talk about the likelihood function. So what is the likelihood function essentially? That's the question. Likelihood function. Then we have to talk about the idea of a maximum likelihood estimator and estimate. Estimator, estimate. Yeah, then we can talk about the log likelihood function. And then we should consider the case of IID data. And then we should summarize that into a three-step procedure. And then we have introduced maximum likelihood, which is of course a very general procedure, and you might still need to think hard in terms of what you do for an actual model. Good, so this is then the content of the next part. So first, the likelihood function. And I think once you understood the concept of the likelihood function, the rest of maximum likelihood estimation is actually relatively straightforward because it's just some technicalities there. So what is the likelihood function? Well, the likelihood function, maybe I first write it in abstract terms and then explain what's going on. So the likelihood function is a function which I'm currently writing on my device. That sounds somewhat weird. So that's a formulation of the likelihood function. So what does it apply to and what's going on? So first of all, the likelihood function assumes that one has formulated a probabilistic model for some data, for data y with parameters theta. So y and theta I deliberately leave up to your imagination right now what y and theta is. It's definitely, they are not necessarily scalar things, and they will often, of course, will not be scalar things. We have already formulated a probabilistic model now in this form. So if you think about what we did last time, we actually defined a probability distribution over data depending on some parameters. So we defined something like that when we defined the GLM in its normal distribution form. So does anyone remember what we actually called it? We wrote y is distributed according to something, or we said py. We did not make the parameter dependence explicit, but does anyone remember how we formulated the GLM at the end of the last session? No one remembers that? You can look it up on YouTube if you want. That's actually fairly important, and you should memorize it. So we formulated the GLM last time as a multivariate Gaussian with expectation parameter x beta and covariance matrix parameter sigma square in. And this, as I also said a couple of minutes ago, implies that we actually here have two parameters, namely beta, which as you remember, is a p-dimensional vector, and sigma square, as you remember, is a value larger than 0. So our theta, in this case, so the theta is actually beta and sigma square. Yeah. So this is the thing that you need to do if you want to do a maximum likelihood estimation. You first have to define a probabilistic model for some data which depends on some parameters. If you don't have a probabilistic model then nothing works. So this is why probabilistic modeling is great. The other thing is, if you want to do maximum likelihood estimation, you need also some free parameters. If you just want to evaluate the likelihood of some data, you don't necessarily have to have parameters, but so that works regardless of whether you have parameters. But of course, you cannot estimate parameter values if you don't have any. Yeah, so that's the working example that you can think of in terms of this p theta y here. Yeah. Now, the important thing in terms of the likelihood function is that you conceive what is written up here, namely the probability of some data given some parameter values, not as a function of the data, but as a function of the parameter. Yeah, I write this in words down. Conceive p theta y not as function of data y, but as function of parameter theta. So this is really, if you want to get started on maximum likelihood estimation, this is the crucial bit. It's a little bit hard for you because just last week you learned how to essentially conceive a probabilistic model as a function of data, and now I'm telling you that you should, for the next step, not do it like as a function of data, but as a function of the parameter. But that's how life is. Sometimes it's cruel. The important thing is, and this is maybe even more general, is that the probability of y given or depending on some parameter value theta can of course be thought of always in these two versions. So you can either ask yourself, what is the value that this multivariate normal distribution takes on if I fix the parameters? So if beta and sigma square are fixed and I put in different data vectors y, what do I get out? You can always think about it like that. Or you can say, I fix the value of y, and now I let my theta and my beta and my sigma square vary around. How does the output change? So it's not that the likelihood function is completely different from the probability, in this case probability density function that describes the model, but it's just it's a different focus. So you either leave the data constant and look at the probability as a function of the parameters, or you do it the other way around. Yeah, we are now concerned, because we're doing likelihood estimation, we are concerned with the case that we leave the data constant and look at the whole thing as a function of the parameter. And this is what is then written up here. So here I'm saying that the likelihood function for fixed data y, yeah, so y is fixed. This is what the subscript means. is a function from a parameter space. This is parameter space, big theta, to the positive real numbers, because in the end what's written, what's the output is a probability density value, or in some cases, in the discrete case, a probability mass value. So it's always larger or equal than 0, cannot be negative. That's the only thing that it says. What it takes as input is a parameter value, which is essentially what I'm saying here, so that you conceive it as a function of the parameter. And how it's defined, so how the value of the likelihood function is defined is, so that's this definition here, is as the probability of the data that is fixed for a specific value of the parameter. Yeah. One thing that is important there, especially if you think about the fixed data, is that, of course, you can, so when we discussed last time, we discussed how we sample data from such a probabilistic model. Yeah, so we did something like we sampled a simple linear regression. So we had a y1, and then we did another simple linear regression, and we had a y2. So these would be different data that for each of which you can write down a likelihood function. That means that if you think more abstractly about it, the likelihood function is actually a random quantity, because it depends on the data that you sample. However, in a given context, so for fixed data, which of course has a high experimental and data analytical meaning, so for the fixed data that you observed, there is one likelihood function which is dependent on the data, but is now a function of the parameters. Yeah? So the likelihood function is dependent on the data, but it's not considered as a function of the data. That's the important point. Yeah. Good. Maybe a little bit on the notation of my p theta y. So sometimes you will find also the likelihood function be written like this, where there's some conditioning on the theta. I do not do that on purpose, because this implies that you actually conceive theta as a random variable. And when you apply maximum likelihood estimation, you don't conceive of the parameters as random variables, so you're not in a Bayesian estimation scenario. So this is why I always use the parameters as a subscript. Yeah, another way to, I leave it at that. There are different ways that one can write this, but so I converge to this scenario. Yeah. Questions so far? No questions. Everything is clear. Good. Or everything is completely unclear and you want to go home. Good. That's the likelihood function. And what we want to do with the likelihood function is to find a point estimate for our parameters. Remember that I discussed point estimates last time. So you have true but unknown values for your parameters, and you try to find a point estimate. So if your true but unknown values are, for example, 2.4 and 6, you try to estimate them by values like 2.6 or 2.5 and 7 or something. But you don't want probability distributions, you don't want posterior distributions, you want numbers. Yeah. And the maximum likelihood estimator, maximum likelihood estimate E, or I will discuss about my language in terms of estimate and estimate in a second, is defined as follows. So with the head, you always indicate parameter estimates, or decent frequentist classical statistics is done like that. Then, because you can do maximum likelihood estimation, but you can also do different kind of estimations, I use this subscript ML. Now, how is that defined? Well, it's defined as argmax over theta in theta of the likelihood function. Yeah. What this means is essentially what we just did for the calculus refresher. So we looked for a value x star that maybe let's go back to that. We looked for a value x star that maximizes this function, and this value x star I'm now giving a name first of all. So I call this the maximum likelihood estimator, and I'm saying that it's defined as the argument of the function. So that's this arg that maximizes it, and the function of interest is of course the likelihood function. So this is the likelihood function. What else? And it's meant to be the value that maximizes this likelihood function over the entire parameter space. Yeah. So this is saying that it's theta in theta. Briefly on the notation, this is where one differentiates between the maximum of a function, which is a value that the function takes on, and a value that maximizes the function as an input, and this is why we use this argmax. So max, in this logic, max L theta, Ly theta, in this logic would be the same as Ly evaluated at theta L. Yeah, just that you're not worried about this argmax. Actually, the argmax is, and the max is even more. There could be much more said about that. So if you're more carefully mathematically, you would actually use the supremum here, and also make sure that you're talking about sets and not single values, because you could have multiple values that maximize a certain function. But so I'm using a quite pragmatic approach that is okay and serves the purposes of this course. Yeah. So the maximum likelihood estimate is that value of the parameter that maximizes the likelihood function. Now, what about my estimator business? So an estimator, just to introduce that briefly, an estimator is actually a mathematical function that maps data values onto parameter values. And we will actually see estimators later, which are general rules how to compute estimates based on some data. By an estimate, I mean a value that actually an estimator, let's call the estimator gamma. An estimate is a value that this estimator takes on for a given data point. That's kind of trying to be a little bit careful with the language, but I'm not introducing these terms from mathematical statistics in a very general and specifically rigorous way. So I will, when I'm saying estimate, I always mean numbers or posterior probability distributions. When I say estimator, I mean a function that takes in data and returns a point estimate or a posterior probability distribution. That's just me. Whether it's not crucial, but because I'm not doing this mathematical rigorous overhead, these terms might live a little bit in obscurity during the course. But I think you can deal with it. And once you start thinking about it, it's actually quite natural to dissociate estimators from estimates. Good. Questions right now? No? Good. Then let's have a break and continue at 11.